Okay, so now you're familiar with relative time, right? My car is older than my dog. The Mesozoic is older than the Cenozoic. Now we're going to talk about absolute geologic time, right? How do we actually put ages, exact numbers to these time periods, these epochs, these eons, these eras? And one way we do it, a big way we do it, is using radioactive decay. Right? Now, radioactive decay requires you to remember some chemistry. All right, so a review of chemistry, review of atoms. An atom is the smallest particle of matter that can exist as a chemical element, right? So atoms are oxygen, silicon, sodium, so on, right? An individual atom is composed of a nucleus, which is orbited by electrons. The nucleus has protons and neutrons. Electrons orbit around that. Now we describe atoms with their atomic number. That's the number of protons in the nucleus. For example, carbon has 6 protons in the nucleus. Or we can describe an atom using its mass number. And this is more important to radioactive decay. The mass number is the total number of protons and neutrons, right? So carbon generally has 6 protons, 6 neutrons, making a total of 12. So we would say the mass number of carbon is generally 12. However, notice I said generally, right? Some atoms can have the same number of protons, but different numbers of neutrons, right? So for example, carbon can have 6 protons, 6 neutrons, or it could have 6 protons, 7 neutrons, or even 6 protons and 8 neutrons, right? All of these different types of carbon are called isotopes, and we call them carbon 12, that's the most common one, carbon 13, fewer, and carbon 14, which is almost non-existent, but does exist. Right? Now, the atoms that have more neutrons are generally not stable, right? They're unbalanced, they're unstable. Therefore, they often decay. Right? So for example, carbon 14, it's unstable, right? It has too many neutrons. So it will decay, it will give off an electron and an antineutrino, which we're not going to get into, but it will decay to produce nitrogen 14. Right? The parent element, that's the original atom, the carbon 14, will decay radioactively to form the daughter atom, the daughter element. In this example, it's nitrogen 14, right? So the parent decays to the daughter. And it does this at a very specific rate, right? The rate is different for every atom, but for every atom, we know a specific rate, which means that we can measure the amount of parent to daughter and know exactly how old the atom is, or how old the sample is, not the individual atom. Right? So as time passes, the quantity of the original parent diminishes, the number of daughter atoms increases, and this allows us to figure out the age of the material. So this graph is showing that over time, the blue uranium parent decays, while at the same time, the green daughter increases. This example is for uranium-238, lead-206. So that if we know the percentage of parent or daughter that exists today, we can figure out how old that material is. So for example, I want you to use this plot of uranium and lead to figure out how old a sample would be if it has 80% uranium, 80% parent, and 20% lead, 20% daughter. Right? Now, the y-axis of this chart says relative number of atoms. Keep in mind that 80% means 0.8 over 1. So on this graph, you are going to find 0.8 on the y-axis. So that's 0.8 of uranium. So you're going to find that 0.8, read over until you hit that blue uranium line, then read down until you find the time in years to figure out the age of this material. And you will find that if a rock is 80% uranium, 20% lead, then we know that that rock has to be 1.3 billion years old. Right, this is just one example of uranium to lead, but there are many, many isotopes out there that we can do these same calculations with to figure out how old is a rock, how old is the Earth.